So maybe before moving to the next topic, I want to mention maybe something super quick about the spin. In case you scatter things with spin, it's basically just to give you an example, okay, how things will work, so you have an idea. So let's imagine now a theory of photons. I'm going to be very quick on this example, but sorry, I got the wrong sign here. Remember, we saw that with the causality, you can bound things like this using the superluminarity argument, FF tilde square, the fourth, and so on. So you expect that using positivity, that use analyticity that comes from causality, you will be able to expect to bound A and B as well with the special relation argument. Indeed, it's the case. The only thing you have to be careful are the polarizations. So, for example, let's consider a scattering of photon with the helicity -1, 2 plus, 3 plus, 4 minus, in the convention that Alex was also using. So this would be, now you're experts on this. So 3 to square divided by m to the fourth, f minus plus, st. So you see that 1 minus indeed has 2 powers of the angle brackets, 2 plus is here, and the rest also matches. Okay? And however, Alex was referring to the standard model where you have only marginal and relevant operator. So this operator you cannot be able to write it. In order to write it, you need m to the fourth in the denominator. Okay? This comes from an irrelevant deformation to a normalizable theory. So in this case, this f here, if you see it, this is energy square, so this is e to the fourth, so it must be a linear combination of these two. This term here, in fact, is, if you do the calculation, this is a plus b. It starts with a plus b. And then there are function s and t next, which is also, by the way, is also symmetric under the exchange of 1 and 4. So it's st symmetric. So this is going to be some u, probably. U divided by m square corrections. So the way you bound this theory is basically to factoring out the little group scaling. Okay, so rather than working with the amplitude, you work with the amplitude stripped. So you work with this amplitude stripped of the little group factor. We divide by this part. Now, and this one will enjoy the same analytic properties as the scalar theory. So you can do your, now you can do your nice contours. For example, in the forward limit, if you take now t going to 0, it means in this language means 1 going to 3, and 2 going to 4. So now you get 1, 2 square, 1, 2 angle bracket square. So this is going to be s square here, right? So this would be the second arc. This is arc 2 basically. This is arc 2. For this now it depends on the helicity configuration, minus plus minus. And you run the same argument, since this one is this one divided by this gives you this. Now has a pole in S, so basically it's dividing this by S, integrating this one like this. You learn immediately that this is going to give you A plus B. And therefore, without any further ado, A plus B positive. Okay, in one shot. No background to be found, no equation of motion to be solved. Pretty neat, right? So, one shot. Now, you can be smarter, and rather than scattering definite elicities, in principle, you can scatter any state. But then you can scatter also linear polarizations. Which are linear combinations of definite elicities. The nice thing of doing this is that, which is still elastic, still everything we did carries through, is the nice thing is that this linear combination you get will involve also inelastic. So I can keep it perhaps like this. No, I don't think, but you think it's this? The nice thing about taking linear combinations is that you're going to pick, since they are written, for example, let me give you an example. So, for example, this one, polarization, linear polarization all up, the amplitude is plus, 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 okay, which is not elastic, this is elasticity flipping. You have plus, plus, because this is a notation in all momenta incoming. So if you reverse the outgoing momenta, it's going to be plus, plus, going minus, minus. It's an inelastic process. So it involves, but the process we are studying is actually elastic. It's just written in terms of inelastic parts, inelastic bits. And things like this, and it keeps going. So since the special ratio for this also is going to give you positivity, it's going to be a linear combination also of the inelastic parts. And the inelastic parts is going to give you A minus B. So if you scatter this one, you do the positivity of this one, integrate this one, divide by this, divided by S squared ds over S, the same. You're going to land in A minus B positive. So combined with this one, you're going to get that both A and B are positive. Okay? I'm going super fast just to give you the flavor, okay, how to do it. But, okay. So being elastic, so you can be elastic in the elicities. So you can do the same elasticity, plus plus going to plus plus, or plus minus goes to plus minus. Okay, but you can be elastic in you can take a linear combination, still be elastic, right? Linear polarization in this direction going the same. There's an elastic process which looks like is a linear combination in elastic processes in terms of the elicities. So you use leverage on this and you learn more. Okay. Okay. So this is the only thing I want to say about spin. In the case you're interested in particle with spin and mass, there are other things to be careful about, but there's not going to be time to discuss this. So let's now discuss the relation. So we have seen that with causality, you were able, with the building backgrounds, to not only say things that were positive, but we were saying that things were actually smaller or larger than other ones, right? So we were saying that C3 can never dominate over C2, which is not quite the same as saying C2 is positive, right? It's more. So this comes from studying positivity and the theory of moments. I'm going to show you how to do it. So let's consider again our ansatz for a 3-level amplitude in the simplest theory, which is the scalar theory. Simplest, at least for these purposes. Sorry, I'm jumping a little bit with notation. Now I'm not going to put, I'm going to normalize the units directly inside these coefficients. These are dimensionful coefficients. Let's consider the arcs. Again, for the time being, again, in the forward limit. So in the forward limit, maybe there's a factor of 2 here in the definition, and a factor of 2 here. So that in the forward limit, this becomes C2 S squared plus C4 to the fourth, and so on. So the arcs are defined like 1 over 2 pi I. The integral, these funny contours, if you want to include IFRed branch cuts, but let's simplify our life and let's neglect loops. Let's imagine that these coupling are small enough that we can trust these operators as they are within a tree-level approximation. So since the convergence starts from when divided by s squared, by the assumptions are gone. Remember, one of the assumptions was the amplitude divided by s squared goes to 0 when s goes to infinity. So we start with 2 here. It's convenient to actually factor that 2 out here. Okay, so now the arcs start with n. The convergence is going to be guaranteed by n equals 0. By the argument we saw before, this just gives us C n plus 2. Okay, before it was Cn over m to n. Now the mass is taken inside the C's, and the n is shifted by 2. So this is the relation. And so this is what I would consider, or I invite you to think as infrared representation of your Wilson coefficient. So you have a formula that says that your Wilson coefficient is an integral you can calculate in the infrared. Okay? It's a calculable thing within the FTT. There is, by deforming the contour, as we have seen before, I can draw it again. We are doing a contour like this with a pole we inserted. Then there is a branch cut starting at m here, m squared. Deforming it is the same as doing this contour. So there is also an UV representation of the same. It's an integral m squared, not m squared, s. The radius s here is this distance. Yeah, I'm going to call this s. So it's where the arc starts, where the infrared effects start to be important, or where the is roughly m squared also. Okay, the theory is weakly coupled as we are assuming. It's not much of a difference. So from s to infinity, ds prime over s prime, imaginary part m of s divided by s prime m plus 2, which is positive. Okay, that's we established, but it's more than that. So let's change variables. Let's go to the following variables. Let's normalize s here. Yeah, you can take as the radius I'm taking. If I neglect infrared loops, I can take it as large as m squared. So you can think of s basically as m squared. Otherwise, this formula is going to hold also with loops included. So that's why I'm keeping s around here. This one, after this change of variables, is nothing but some so it's a nice integral on a compact region from 0 to 1 of something positive, a positive measure. So this one times x to the n. So this is not the form, integral over a positive measure, the new x, between 0 and 1 of x to the n. Okay, this is a moment of a distribution, of a positive distribution. Okay, so yesterday with the shirt was better. And so there's a connection. So this is what I would call the UV representation or the Wilson coefficient. So you can calculate it in infrared through the infrared representation, and it must be the same. Yeah, I put it on top. Now I should hold. Yeah, thanks. But is basically Wilson coefficients are moments of positive distributions. So why is this useful? Up to, sorry, there's a prefactor here which I want to keep it around. Let's write it here. I'm going to call it mu n, or x to the n, okay, both, which is certainly positive because the integral positive distribution, but you can gonna say much more. For example, one thing that you can say immediately is that x here is integrated from 0 to 1. Okay, so x is smaller than 1, positive and smaller than 1. So x, the moment n plus 1 is smaller, integrated against a positive measure, is smaller than the previous moment. So mu n plus 2 is going to be smaller than mu n plus 1, it's going to be smaller than mu n, and so on. It's monotonically decreasing. Okay? Therefore, your arcs are monotonically decreasing up to putting the right units. Okay? So arc n, now of course, we were saying these are, where are they? Here, they are these guys. We are just basically saying that C n plus 2 times s to the n plus 2 for n even, which are the ones we are discussing, is monotonically decreasing. So this in particular, this one is going to be smaller than Cn s to the n. So it's never possible that C4, this term here, is going to dominate over this, even though you would have a symmetry that would enforce that example, right? You would have the shift sim, the very strange shift symmetry I was discussing that with suitable numbers, like something like this, or just by fine-tuning. Imagine this is very small by fine-tuning, right? Is that possible? No, it's not. It's never possible. So starting from s squared, all terms that can have to give a smaller contribution to the amplitude. You cannot have one which is accidentally larger. No, the moment says possible. Of course, for lower than s squared, it's possible. You can have a very large. You can have a large, for example, quartic. Another comment about this is that you get, since s squared in a weakly coupled theory can be pushed all the way to m, s can be pushed to m squared without encountering singularities which are strong. This is basically telling us an upper bound of the cutoff, on the physical cutoff. It's telling us Cn over Cn plus 2 times s squared, which now I'm taking it roughly to be m to the 4th, must be smaller than 1. So it means that if you measure two consecutive Wilson coefficients, you have you know an upper bound on the cutoff, on the physical cutoff, not the strong coupling. Particularly, they can be arbitrarily coupled. Notice it's a ratio. The amplitude can have an overall suppression, could be an epsilon here. The strong coupling can be way, very far. It drops. It's enough to measure the ratio of two consecutive that survive in the forward limit to get an upper bound on the cutoff. That's, I think it's very natural. If you think about it, Let's be simple mind. Just 3 levels exchange. You have a coupling here, and a mass exchange here. Some heavy guy. It doesn't matter how small the coupling is. New physics are M, regardless of the size of G. That's what we are saying here. The ratio 2 consecutive here is not controlled by the coupling. The couplings are overall. The ratio is controlling the ratio of expanding this propagator. You have k squared minus m squared, g squared. So if you expand this, you get leading, then you get next to leading. Doesn't matter the coupling. The ratio is given by this one over this one, or this one over this one. Okay? It's the energy over the mass scale that matters. That's what this bound is about. Sorry, say it again. The mass, sorry, you're referring to the mass? Yeah, but yeah, but you see, you can recast it in terms of the mass. You can put the mass back, which is actually the next comment I wanted to make. So let me do it, specifically what you're suggesting. We can also phrase it in another way. So let's put the mass back, exactly as you're saying. So you're going to get, I'm putting the mass back. So now these G's are defined like with the mass. Cn is Gn divided by m to the 2n. Okay? Putting it back, I'm using the G's. Plus G6. So what we are just basically saying, this bound here is just saying that this is smaller than 1. This is smaller than 1. Okay? It's basically saying there's never a regime where the eigenderivative term, even accidentally, could dominate. No, there's no fine-tuning, no accident where this one could dominate over this one. Crucially, is because we are starting from S squared. Okay? Instead, it can definitely happen that, for example, for the Lagrangian, let's do an example which is not of this type. Lagrangian, you get so the quartic is small, so you have is epsilon, because these are pseudo-Goldstone bosons, right? Suppressed by so in the limit, Carrier symmetry becomes exact, this goes to 0, this is small, and then you have a correction from, so it goes like E squared over F squared, the pi decay constant. So definitely this one, the eigendimensional dominates over, it would be dominant. It's not dominant because it's suppressed by a symmetry. Okay? So crucially is because you start from E squared. Here instead we start from E to the fourth. What we are saying is that from these things can happen only up to E to the fourth. From E to the fourth onward, they cannot happen. Okay? So this provides a boundary how inventive / crazy you can be with model building. Can I cook up a symmetry such that I haven't seen new physics because it starts with dimension 12 at LHC? No. The latest, the leading operator must be dimension 8. Okay? I think it's very important lesson, especially to us, very inventive theorists. So this is just the tip of an iceberg associated to the theory of moments. Okay, now I'm going to regret what I'm saying. There are infinitely many bounds that you can derive from the theory of moments. Questions? Before, perhaps? Questions? Yeah, you can. I just say that there is no theory that realizes that symmetry that's unitary and causes. For example, if you break, if you are in Euclidean, no problem, you can do it. Symmetries are not enough. That's one of the messages. Symmetry is one direction, causality is another direction. the intersection for a certain symmetry may be non-existent. Can be empty. Yeah, that's what I was providing. This example here, you shift your pion field by this, will kill the first n derivative -1 terms. Yeah. No, you can, if it was a simple shift symmetry, this one, yes, because this one selects this operator as leading. It kills the previous one, so it's good. That one, yes. If I'm more inventive, try to fine tuning, having this one starts before this, more important than this one in certain regime, no, that's not going to happen. There is a symmetry, but that theory in the UV is not causal. So you can write down a theory, sure, it's not causal. So another thing about the theory of moments binds you is that you get nonlinear constraints. For example, so we have a measure, d mu, from 0, 1, and we are saying that integrating against xn gives us, this is proportional to the Wilson coefficients we are interested in, right? That's what we are saying. So let's define basically a scalar product. I mean, that's maybe not the most efficient way to doing it, but let's take polynomials. Let's take a polynomial in X, okay? And polynomial that lives in the interval between 0 and 1. And so linear combination of the polynomial are still polynomial in the same interval, so it's a linear space. I can define a scalar product through the measure that I have, okay? Bear with me. Okay, well, why am I doing this? So in particular, I can take the monomial. The monomial is a particular polynomial. Let's do this. So it would be the integral of d mu xn plus m. So in particular, would be proportional to Cn plus m if I take them even. But we know Cauchy-Schwarz. This must be smaller. The scalar product. This one is C to n. This one is proportional to C to n. So we're going to get a relation that Cn plus m squared must be bounded by Cn to n, C to m. So in particular, if you're careful about all the factors, yeah, because remember, actually there was a factor, there was a shift of 2 here, right? The way we normalized it. I'm not looking at the notes, unfortunately. So this is C squared m plus m plus 2 is bounded by C to n plus 2, C to m plus 2 for n and m even. So in particular, for example, take n equals 0, m equal 1. This is implying immediately that C4 squared, you get from here, 2n, m equal 2, sorry, it must be even, m equal 2. C4 square is bounded by C2, C6. So has to be even to, so this one I can define for any n, but to be the Wilson coefficient is for the, otherwise in general it gives me an arc, but it's not the Wilson coefficient in the forward limit were only the even ones. You see? Were only even powers. That's all. So it's just this. No, it's 2m because a scalar product here is this one, this scalar product here is the integral of d mu 0, 1 x n 2. So it's the moment, so this is proportional to C to m plus 2. Okay, thanks. So this, together with the monotonicity that we established before, which was C4 m to the fourth less than C2, C6 m to the 4 less than C4 less than C2 over m to the fourth. Draw the following allowed region. Let's draw them. C4 m to the fourth divided by C2, C6 m to the 8th divided by C2. So there is a boundary here. This thing cannot be larger than 1 by monotonicity. Okay, so this region is gone. So not only is positive, but this ratio cannot be too large. Now there is this one also. You cannot exceed 1 here also. Then C6, this one in this plane. There's nothing saying that you cannot exceed this line. So you remove actually this part. Now there is the nonlinear constraint, this one. Right? If you divide by C2 square, both sides, you get C2 square here. C2, and you plug the m to the fourth here. You multiply by m to the 8. You recognize that this is saying that C6 this combination has to be above a certain parabola. Has to be above the parabola. This is gone. So positivity is value much more in this way. Not only have to be positive, you have to be this finite region. These are called double-sided bounds. Okay, so not only things have to be positive, they have to live in definite, nice-looking shapes. So in our community, yeah, in our paper, we call it this the banana plot. But, okay, well, yeah, maybe it's not appropriate, but anyway, so the it is what it is. So I think it's very powerful. Okay, so what I want to say is that this method is very powerful. How much time I have? Ah, great, fantastic. Questions? Don't be shy. I think, I mean, we are here to answer your questions, so if we at least try answering this. Yeah, suppose you have a model that depends on some parameter, but in that parameter, it moves you around here. Then, so you're asking whether I can populate all of it? Mm-hmm. So you're saying that perhaps being in a particular region here would suggest you are tuning. I mean, that's very, very interesting. No, so I don't think, as far as I can tell, there is not clear. It's not obvious that certain regions here are correlated with fine tuning or not. Okay. There are certain things that you can say about the boundaries, how you can reach them. For example, to be on the boundary, you need a certain amount of number of particles in the UV, things like this. But these specific features, but they are not really tuning, just properties of the UV. You need at least 3 particles. Or the coupling, the ratio of coupling cannot be separated too much. But it's never a cancellation between things that doesn't look natural. At least as far as I played around this question. Which is very interesting, I think, because you're basically asking, can we learn from positivity something about the, for example, the hierarchy problem, something about resolving a fine-tuning issue? It's a very important question. Yeah. So let me make the following observation. To start more bounds, So suppose I give you a polynomial, explicitly, I give you a polynomial which is positive. I tell you this polynomial is a sum over certain coefficients, x to the n, and I construct it such that it's positive. Okay? One stupid polynomial, x squared, plus 1. This is a polynomial. I give it to you. It's positive. So this measure is positive. This is going to tell me that I have a linear combinations. For example, I do it only for n even. Okay, simplicity. So this one is telling me that n plus 2 is going to be positive with known coefficients. The interesting thing, this example is not very informative because this one was already giving me C4 positive, this one was giving me C2 positive. So sure, a linear combination with a plus is going to be positive. What's a big deal? Yeah, but so let's take another better example is this one. This is also positive, but this is a relative minus sign when you expand it. So you get linear combinations with negative sign that have to be positive. So you can extract more. Okay? So the all bounds that you can extract are in one-to-one correspondence or constructing positive polynomials which are not obviously positive. Okay? So the space of all positivities, at least in the forward limit that we are discussing, is equal to the space of is equivalent to find the space of positive polynomials in the interval. Now there's a bit of mathematics which actually solve this problem, characterizing the space of positive polynomial on algebraic set like this one. There's a general theorem called sum of square theorem. I mean, no, maybe that's not the name. That's the name I think myself for this theorem. So sum of square theorem by very recent, well, 30 years old by Schmutgen, which is written in 1991. It's a theorem in algebraic. I mean, it was an open problem until then. Classify the space of positive polynomial. Not in this set. In a more complicated set in higher dimensions. So this is a very powerful theorem. It says the following: the space of polynomial, also in more variables, which is going to be useful for finite t next, which are positive in a domain, which is itself domain subset of Rn, which is specified by certain polynomial being positive. This space is equal to the sum of the polynomial you use to define your domain, multiplying all suitable forms, all arbitrary number, times the squares of polynomials, times p squared of x. Okay. I mean, it sounds a little bit obscure, perhaps. I'm just saying. A positive polynomial is certainly given by a square of a polynomial. Okay? Trivial case. Now, if you define a domain by using a polynomial which is not obviously positive elsewhere, this defines, let's be maybe specific. This domain here is defined by the following two polynomials. Q1 equal x, positive, and Q2 equal 1 minus x. So the first condition, the monomial x is not positive everywhere. It's positive only here, on the positive region. This one is positive in this region. The intersection is the interval. Okay? It's generalized. So you can say in arbitrary dimension, let's define, for example, you can try to define with another, say you want to define the property of polynomials in this region, define suitable choice of polynomial. It can be also complicated things, okay? So So you define this way, then the space of all positive polynomial inside the space is given by this form. So it includes the squares and includes these which are not obviously positive in general. Look, x and 1 minus x are not positive. But on this domain, by construction, they're positive. So this is certainly positive. And this exhausts all possibilities. So why is this? Well, this classifies all possible polynomials which are positive in a given domain, and therefore it gives us all positivity that you can extract in the forward limit. Let's keep the figure. For example, so let's take the polynomial constant 1 on the interval 0. So let's consider our case. So polynomial 1 is positive. So integrated over the measure gives us C2. Okay, positive. Now, next, x is on the basis. I can take arbitrary products times 1, for example. So x to the n. I get Cn plus 2 positive. So these are getting what we knew. Now we're going to get something that's, bear with me. Let's prove this one. X to the n, which is positive. So remember, we're integrating between 0 and 1. So 1 minus x is positive in this domain. Indeed, is one of the bases. So according to the theorem, is allowed. Indeed, I mean, this case is obvious. You don't need that theorem. Okay? But generalized to eigendimension, which is useful when we do the finite later. Let's get familiar with the simple case. So this one is just telling you that C, all of these, of course, I'm assuming n even. Okay, n even, such that I can put equal the Wilson coefficient. Now this is telling me Cn plus 2. Okay, no, maybe this one is not a good example. Yeah, we need to put this one. Yeah, it's okay, this one. 1 minus x squared, which is 1 minus x, 1 plus x. So this is positive, this is positive, this is positive, so this is good. So this one is Cn minus 2. Yeah, so in my notes, sorry, I had it wrong, but this is minus Cn plus 4 has to be positive. So it's the monotonicity condition we were saying before, right? I increase the Wilson coefficient, it has to be less than the previous one. Now, let's get also the, for example, let's get very simply this banana plot. So let's take a square. Now let's take a generic polynomial, Pn. Let's square it. So xn, sorry. Okay, so integrated over 0, 1 d mu. So this is equal. And let's take even powers. Okay. So we're going to get g to n, g to m. For any this is telling that this seen as a matrix elements is a positive definite matrix. Okay, so it's telling us the Hankel matrix H and M of elements mu to the moment 2m plus 2m, which is equal to C2n plus 2m. Yeah, okay, I'm dropping all the factor of S. I didn't put them anymore. Okay, so I basically set S equal to 1 everywhere, but with power of S all around. So this must be positive definite matrix. So let's see it. For example, mu0, mu2, mu2, 4. To be positive definite, this matrix must have positive eigenvalues. So it means this is positive, and the determinant must be positive. So you will have first moment positive, we knew it. Mu4 positive, we knew it. Now we get mu0 times mu4 minus mu2 squared must be positive. This is nothing but C2, C6 bigger than C4 squared. The one we are trying to, which is this one. Okay. In fact, you can show this is the optimal bound. If you project only on the first 3 Wilson coefficient, this is the optimal shape. You cannot do better than this. All the other constraints will involve Eiger moments. So when the projection will kill them. Questions? How much time do I have? 10 minutes. Okay, then I can say something about finite T without finishing it, but I'm going to say some moral message about it. Questions before moving to finite T? In the notes, there will be a detailed discussion of finite T, completely worked out. So I encourage you to go through, reproduce it. Now I'm going to show you a simplified version that I'm able to finish in 10 minutes. So let's turn on T. So now our ansatz contains all Wilson coefficients are known. And let's work in the complex S prime plane of finite T. So we center it around the point, the cross-set symmetric point, which is 2m mass. Let's set the mass to 0. So the cross-set symmetric point is minus T over 2. And we're going to take T negative, so it's going to be somewhere here, okay, depending on the size of T. So we're going to do our contour. It's going to be a branch cut. With the radius S. So we're going to calculate arcs. It depends on S, the radius, and depends on T. Okay, and like before, you can just calculate it. This in the infrared. This is an infrared representation. Something that is taking place here in the infrared, so you can calculate it with your ansatz. Okay, so just taking the residues in S around S equals 0 of this. So for example, let's see what changes. For example, this one contains U squared. U is minus S minus T squared, right? So what I want to say, yeah, this one doesn't change anything basically. The first that is, yeah, this one is interesting. So this one is minus S minus T. So it gives you, this term gives you C3 minus S squared times T, then plus a term with the one less S, one more T, right? Plus S T squared. Basically. So you see when you calculate, for example, now arc at 0, which take the residue, so you remove the S squared part, Now, not only you pick this one, but you pick also a little bit from this proportional to t. So the arc 0 is going to be C2 minus C3 times t. The same here. If you expand this one, the various product, you're going to get s squared times t squared, s squared times u squared. So it's going to contain an s squared term. It's going to correct the arc 0. So it's going to contain, for example, in this case, plus 3 C4 t squared, and so on. And likewise for the others. So arc 1, st, something that you can calculate in the infrared. You have finite t corrections to whatever we have said before for the arcs. Now this is for what concerns the infrared representation. Now we define the contour. We write it with the UV representation, which now is going to be 1 over pi. So I'm skipping the steps, so believe me. So let's say for, arc n is prime. So is the discontinuity now at finite t, which is not necessarily positive. Maybe it's in a second. It's positive at t equals 0. It's not at t finite, it's not positive. And before we had the 1 over s to the n plus 2 plus 1 that now I put it here. There was a 1 over s, that's I put it here. And these two terms were combining. Now with finite t, they are no longer combining exactly. When I do cross-section symmetry to map this one to this one, there's a reminder which is given by this factor. Okay. So there are some negativity that may come here and may come here. But the point is that we know through the partial wave decomposition how much negativity we can get. So let's span this in partial waves. So now the partial wave, the imaginary part of the partial wave, this is positive. Again, by unitarity projected on a particular basis, the basis where you diagonalize the angular momentum. The regional polynomial is 1 at t equals 0. It's no longer positive in general, okay? Regional polynomial. So, by the way, it's a polynomial in this variable. As a function, this is the cosine, the scattering angle. So it takes value, so P0 is this, P1 is this, P2 has 2 nodes, so it's this, and so on and so forth. So you see they cross. Only the first is only positive, this one is already negative from this part onward, this is negative, and so on. Of course, for very large S prime here, which is integrated, it becomes positive again. But you have to control this negative contribution a little bit. So there are two strategies to control the negativity coming from this part and from this part. One is to integrate against suitable found functions. So integrate this against some function of t, multiplied by f of t. suitably chosen, such that when it's integrated against this known polynomial, this is a known polynomial, this is a known function, you require that what you get is positive. That's possible. You can find this numerically, for example. Okay? That's possible. That's one strategy. Another strategy is to expand. You know this polynomial, you expand it in T, you expand this also in T, and you match it to the dependence in T that you get here. Okay? You get an expression that is coefficient in terms of linear combination of moments. Some become with negative coefficient, so some of these guys, C3, may be a little bit negative. Okay? That's the part, this second strategy is the one that is discussed in my notes. The one which I will not have time to discuss, even though it's there. Okay? So I encourage you to have a look. But there is a simplified version of this, which gives you an order 1 bound immediately also for the coefficient that vanish in the forward limit, for which the forward limit was not good enough to put a bound on, which I'm going to tell you about in a second. It's very, very simple. And maybe before that, basically, the idea here is that the second option that you expand in T is to interpret this integration and this as a moment problem in 2 variables now. Is a sum over the angular momentum, integration over S, over a positive measure. So this defines a 2D moment problem. So now you have a 2-dimensional measure in X and L, and the problem become finding all positive polynomial in these 2 variables. You get a linear combinations. What is linear combination? How much is bounded? So it's something that you can treat mathematically is a pretty simple. I mean, okay, maybe not super simple, but it's a generalization of the 1D moment problem that you can manage. Okay, it's not incredibly hard. The logic is similar. You recast it as a 2D moment problem. 2D moments have properties, and you use them to derive the positivity. So, in the lack of time, instead, let me present to you the super simple method, which is quite good enough, which is the following observation. So let's rewrite this in the following way. Let's do it in the simple case, arc 0. Just rewriting that for the arc 0, and just very explicit. Okay. Now the observation is the following. This can be a little bit negative because of 2 sources. This one and this one. If t was 0, this would be 1. This one would be 2. With 1/2 would be 1 also. And the leftover would be what we had before, would be the arc 0 at t equals 0. Okay? So we have to control how negative this can possibly be. It's very simple. Legendre polynomial is never more negative than -1. Right? So the modulus for arc 0 st is bounded by setting this monotonically, so it gets the largest, so monotonically decreasing gets the largest value at s prime equal s, so I can pull it out at that value. So what I get is that at s prime equal s pulled out. And then the rest is over pi, sum over n, plus 1, s infinity, ds prime, imaginary part, and s prime. This one is bounded by 1, to This 2 I can put it here, over S prime square, which was S prime cube. So you recognize that this is arc 0 S at t equals 0, which was positive. So arc 0 S t is bounded. Units of the arc at t equals 0 can be negative, but not too negative. It's bounded by a known function. This function here, which for t0 is 1, for t small, it's going to be close to 1. Okay, so this is a true bound. It's an approximation done. It's a very crude bound relative to the bound that you will get with moments. This is good enough actually to get the bound on C3, for example. Now let's put a bound on C3 with this approximate. No, this is an exact bound. Now we're doing an approximation. So let's imagine the Galilean symmetry is a good symmetry, and let's run a contradiction. Let's imagine that this is much larger than this one. Okay, the arc 0 is this, finite t, at t equals 0 is C2, and there I'm taking the ratio. So I'm taking this one divided by C2. So the left-hand side here is 1 plus C3 over C2 t plus square. It's bounded by this quantity here. Let me call it A square. Okay, so far so good, no approximation yet. This is still an exact inequality. This for t, not too far from I mean, reasonable t, like minus one half units of s. This is order 1, but by assumption, I wanted the amplitude to be dominated by C3. This one, by assumption, I'm assuming Galilean symmetry was good. This is supposed to be, so this one dominates over the 1 squared. So this is saying I have something that grows quadratically in t has to be less than something that's basically constant. So there's a maximal t where this, so past a certain t, this can no longer be true. Okay, so you run a contradiction. This basically is impossible for C3 to dominate over C2, even though you have a symmetry 4. Okay. Now, if you run the 2D moment problem that I was alluding to, the exact bound that you get, so this is just saying that it's impossible, but it's not very quantitative. You can also be more quantitative. You just draw, I mean, it's a parabola. This one is a known function. You see when they merge, you use a sheet of paper, let's see, counts the separation, and you get a bound, okay? But you don't need to semi-definite program to do it. And if you do it with the moments, you get C3 as cube is bounded by 3/2. So if you want M, okay, as cube, 3/2 C2 square and minus 8. This is not the optimal bound. It's the simplest bound you can get in the simplest bound that you can get with the two-moment problem. So it shows you that it's never larger. Can be negative. Can be negative. No, there's no problem with that. But it's never dominating the amplitude relative to the C2 contribution. Perfectly consistent with the causality story that we ran the other day. That if C3 was dominating, we ran in a causality with an issue with able to be the background where the perturbation were propagating superluminally. Okay, now you get very sharp bound. In the causality argument was an order of magnitude bound. You can have it dominate. Here, very explicit, 3/2, 8. Okay, very concrete numbers. Okay, I think with this, I can stop. And are there questions? No, unfortunately, that's the weak point of all this program, is that it starts saying something about the very relevant operator from the. So you need to, the leading is pretty relevant. So yeah, so it doesn't tell you something about the irrelevant. For example, it tells you in the photon theory, this is the first operator that contributes to the amplitude, dimension 8, very relevant, boom, positive, immediately you get it. Okay. Instead, in QED, marginal operator doesn't say anything. Of course, charge is not constrained. For example, the same argument, you can use it in gravity. Riemann to the fourth, this has a lot of derivatives. So as 8 derivatives, this grows like s to the fourth. Okay, this is positive. Okay, and so on and so forth. So, but only quite irrelevant operator. That's the real limitation of this is to find a place where yeah, still interesting. So I think, for example, Alex has a couple of beautiful papers where he studied the space of large QCD scattering of mesons, and even though the bounds are on quite irrelevant operator, they obtain very interesting results. Likewise, there's a paper by Simon Carruot and Gupta Martinez, David Samos-Duffin, and I hope I'm not forgetting someone, which is great about gravity. Okay, they show that, for example, in this talk, okay, maybe something very important that I forgot to tell, which is important. This works once you give the effective theory. Remember, the first rule of effective theory, specify the degrees of freedom. So if these are degrees of freedom, those follow. You can break this bound if you forgot 1 degree of freedom. For example, you forgot gravity, well, in certain cases it matters. Okay? So if this coefficient is teeny tiny, you turn on gravity, it may undo a little bit its positivity. But only if this is teeny tiny, is gravitationally induced. So, okay, you're integrating stuff which has only gravitational coupling, things like this. Of course, you can always imagine that you want to take a limit where your QFT in the UV is well defined, decoupling gravity. Not that it makes sense only because gravity is around. So this one should survive in the limit I'm going to fit. But it's a caveat. So given the effective theory, so specify the light degrees of freedom, the bounds follow. The only way I know to break them is changing the infrared. The great things about this is that this is IR sensitive and UV insensitive. Doesn't matter what you do in the UV, they hold, but it doesn't matter what you do in the infrared. That's great because we live in the infrared. We can learn about things. Yeah, and then there are a series of papers by great people about this, so and encourage you to have a look. The questions before I say goodbye? Okay. So thank you very much for your attention. It was a real pleasure to teach this school. I was delighted to be invited, and the place is amazing. And I hope you will be able to extract some information from the lecture and the lecture notes. And if you have questions, I'm here until tonight. So tomorrow